Now in today's class we shall learn about angular quantities in circular motion. Now first of all, let me tell you that we have already learned about motion in a straight line of a body. So if we can recall a few points from there, suppose this is a straight line path and here is the block I take onto the straight path. And as the block moves along the straight line, goes to another point, you know that I can choose my coordinate system with a single coordinate axis. This may be my origin, I call it O, and initially the position that you can find out just by measuring from this origin, if the distance was x1, I could say the coordinate of the block initially was x is equal to x1, and similarly if you find the next distance from the origin onto the final position is x2, you can call that position to be x is equal to x2, and you could find out the displacement of the body, that is this distance that was traveled along the straight line. So if I call say delta x as my displacement, if delta x is called my displacement, delta x is simply given by the final position, that is x2 minus x1. The advantage of this method is this, or for this case is that since the block is moving in a straight line path, we just require a coordinate system comprising only one axis, that is the x-axis and the origin, and you can express the coordinates of the body in terms of a single coordinate, in this case is x, and correspondingly you can find the displacement by taking the difference between the final and the initial x coordinates. So a question might come that the circular motion of a particle about a fixed center, can we treat it in terms of a single variable, a single coordinate? Obviously, initially it might appear this is not possible. Let's see the cases. I am just here considering a coordinate system, and here we can just name it. This is the origin of the coordinate system. This is my plus x axis, this is minus x axis, this is plus y, and this is minus y. Now this type of coordinate system comprising two axes cutting mutually perpendicularly and with an origin is called the Cartesian coordinate system, the right-handed Cartesian coordinate system. And suppose a particle is located on this coordinate system at P. So you know how to choose the rectangular coordinates of this point P. First of all, you drop a perpendicular from the point P on the x-axis, and similarly on the y-axis you draw perpendiculars, and you see that this length is found to be x and this length is found to be say y. So you write the coordinates of the point P in the Cartesian coordinate system is x comma y. Obviously x and y are standing for the lengths of the distance of the foot of the perpendiculars. As you can see from the figure, I draw perpendiculars. Let them call them, say I call it PM and PN, and then the length OM if it is x, then that is the x coordinate, and the length ON if it is y, that is the y coordinate. So that is the way you define Cartesian coordinates. Let me draw on the same figure another type of coordinates called polar coordinates, plane polar coordinates. For this, what we can do, I can just join the point O to the point P with an arrow as we have seen here. Now this length of course is my R. I'll take this length to be R, and the angle that the OP is making with the positive x direction, the angle being measured anti-clockwise, that angle is called theta. So we could write the coordinates of P in the polar coordinate system in plane polar coordinates, that's coming out to be r comma theta. So how do we measure r? We just join the point origin to the point whose coordinates have to be measured, that is point P here. The length of OP was found to be r, and this OP, this line, this vector you can say, makes an angle of theta with the plus x axis, the angle being measured anti-clockwise. So these are the polar coordinates of the same point P, r theta. So let's compare this. X, y are the Cartesian coordinates and r, theta are the plane polar coordinates of the same point. We shall discuss about the conversions later, but I want to tell you that these polar coordinates will investigate. Are both of them changing in circular motion, or at least one of them is remaining constant? That is my next topic. So for this I have just drawn a circle, that is a circular path followed by a particle, say on the xy plane. So let me name this coordinate system. This is just like before, I can call it x axis, and this is the y axis, and that is the origin of the coordinate system. This is Cartesian coordinate system. I have taken the center of the circle coinciding with the origin, and suppose a particle is moving in the circular path like this. So this is the point, this is a particle rather, this point or particle P is traveling in circular motion anti-clockwise, as you can see by this path. So here I have put those two figures side by side and investigate whether the Cartesian or the polar coordinates vary with time or not. Now, as you are aware, you can see by simple comparison that for the point P, the Cartesian coordinates were x, y, and you know how to get that. You just need to drop perpendiculars. Now this is your x, this is, I have already shown the meaning of Cartesian coordinates. This was M and this point was taken N, and you know that this length is x and this length ON is y. So you can easily see as the particle P is moving in the circular path, let me choose any other position. Say it has gone from the position P1 to a new position P2. I don't want to congest my figure, but we can easily see that if the coordinates here, I could write x dash, y dash, Cartesian coordinates. It's easy to see that x, y and x dash, y dash are not the same, because when the particle has come here, correspondingly, if you could have dropped perpendiculars, then these perpendiculars are going out to be this and then this. So you have your new points. This is the foot of perpendicular, this is M dash, and this is your N dash. And if you can find out the length of OM dash, that will be your x dash here. And similarly, if you could measure up ON dash, that will be your y dash here. It's obvious, as the particle has gone from P1 to P2, the values of both x and y coordinates have changed. So in circular motion, both the rectangular coordinates x and y continue to vary with time, and hence that's not really very helpful, not very convenient. So let us go now to the polar coordinates of this point P and see whether both of them are varying with time or not. Now when we investigate the polar coordinates of the point P at different positions, first of all what we have done is that we have joined this origin O to the point P1, the initial location of the particle P, and then we joined also OP2, where P2 is the final position of the particle P.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.